Okay, so I'm going to explain this basic fundamental algorithm, this paper online large margin training of dependency parsers in 25 by Kramer, Kobe Kramer, and Ryan McDonald and Fernando Pereira. And so this lecture is about projective case. We are limited to projective case, but we will extend it to non-projective case in the next lecture, again by the same people. So the paper focuses on projective case only. You know, these edges are not crossing each other. Everything is simple. And we present a new approach to training dependency parsers based on the online large margin learning algorithm of Kramer and Singer. And so following edge-based factorization of Eisner, we can always factorize and write it as this summation. We want to obtain W. But you know, feature engineering is hard. It takes time. You have thousands of features. So obtaining, for example, one feature could be like this. Of course, most of the time we work with part of a speech, because in this way it creates billions of features. So it's not easy. But part of speech has at least some structure. Terminology. We define dt of x to be set of possible dependency trees for the input sentence, and best as the set of k dependency trees in dt. So best is just the subset of dt of x. Because we want to take k out of that, we need these k constraints. You will see why. So parsing using Eisner algorithm, you know that this is a standard way. It's very similar to CKY. It is bottom up, and it is nice just for projective case. And for training, we use online learning algorithm. But this step, look at this step. We are updating W. So online algorithm is different from what you do in batch modeling. You train usually using batch in your PyTorch, but here we are using online. So as soon as we receive the data, we learn it. We don't create a batch in order to learn all of them, because it takes time. So online is fast, and in some cases you have to work on online. So the only challenge is modeling this part, this line 4, and for that we use a mirror algorithm. So we model, so when the difference of scores, this is the difference of scores, y prime is the predicted tree, y is the tree, goal tree, and x is your sentence. So when the difference between the scores is high, we expect that the loss to be high. When everything is fine and the loss is very small, we expect that the difference between the scores are small. So we are regularizing among all possible solutions to these area. And because W could blow up, so we minimize W, we restrict it. Otherwise, W could become infinity, and we don't want that case. So this is the standard case. It was generalized for multi-class classification by Taskar in 2013, but we don't need this. What we need is not minimizing W, but the difference of W in different iterations. And the problem that we have is that this constraints that we should do this for all y prime. You know, we have exponential, many possible trees. How do you do that? For that reason, people said, okay, we just stick to the k-best trees, and we are restricted to that. Even then, after that, people noticed that even k is too much. K should be 1 in order to be fast. And so now we know how to update our w, because this is just a simple quadratic optimization, and we can do that. But a different approach is to model like this. And what is important is your features. If parent is head, this P, parent, this C is child. So parent word, parent part of speech, child word, child part of speech. These are bigram features that you could use. For unigram features, you just use parent part of speech, parent word. You don't need the word after that or the word before that, like this. +1 after that, -1 before that. So +1 is here, -1 is here, the word here, and use part of speech to create different features. And there are amazing scholars